Thank you everyone for coming this evening. This is our first in-person lecture of this year, so we appreciate this. Please be forgiving. This is only my third in-person lecture I've hosted since I started 3 years ago. I'm going to introduce myself. My name is Galen Kinsey, and I'm the scheduling coordinator at UC White Mountain Research Center. And before we begin, I have something important to say. At the beginning of all of our talks and events, we give a land acknowledgement. And the White Mountain Research Center acknowledges the Numu and Newe as the first people and traditional land stewards of Paihunadu and Koho, the Owens Valley and White Mountains. As a facility managed by a land-grant institution, we pay our respects to the elders, our relatives, relations of past, present, and emerging generations. And just some housekeeping items. I ask that you please silence or turn off your cell phone. If you need to use the restroom, we have a bathroom trailer outside, and one of our staff can assist you with finding that. Some of the buildings aren't marked very well. I will have Tony give his presentation, and then we'll do a Q&A session after the presentation. And then you're welcome to help yourself to coffee and tea in the back, and we also have some new newsletters and stickers and other items for you. If you're interested in learning more about our future events and what we do, we have a sign-up sheet for emails and opportunities to volunteer. So with that being said, I would like to introduce our presenter this evening. It is Dr. Tony Phillips of, I believe, Aspendale?
Yeah.
And he is a science writer and a local science educator, and it's Earth to Calculus Science. Is that correct? The high school program you were leading?
Earth to Sky Calculus.
Okay,
yeah.
I'm so sorry. So you do research with stratospheric data collection and solar magnetism as well. And tonight he will be presenting on how to see northern lights in the Eastern Sierra. Go ahead, Tony.
All right, thank you, Galen. Well, we're going to begin the talk with an existential question. Why are we here? Well, for the answer, you have to go back to May of 2023. And I was up on White Mountain Road with a team of sled dogs, and we had just come up to this giant 12-foot high vertical snowdrift. You remember how crazy last winter was. We were trying to think, how in the world are we going to get over this snowdrift? Well, all of a sudden, this big, beautiful snowcat rolls up, and a really kind man, a bearded man, stuck his head out the window, and he said, "Hey, is everything okay?" And I looked at him. The dogs seemed to like him. I said, "Hey, can you give us a lift?" He said, "Sure, on one condition. You have to come speak at the White Mountain Research Center." So this is where your speakers come from. So Stephen gave us a lift. There's my dog sled on top of the snowcat, and that's CJ right there, one of my lead dogs. And we spent the day. Hey, don't make fun of me for just sledding with 3 dogs. We spent the day sledding along the crest of the Whites, and for that reason, here we are. So I have another question for you. Galen. You forgot one. Don't change it now.
Sorry.
How many of you have actually seen northern lights? Okay, so a handful of people, and I'm guessing since you're here, you're interested in seeing northern lights. A popular misconception is that you have to travel to the poles, to the Arctic Circle, to see northern lights. That's why they're called northern lights. But actually, that's not true. This is a picture. The background of this is a picture which was published in the LA Times last March. And it's the Aurora Borealis over Mammoth Lakes. Okay, that was, the date's wrong, but it was March 23, 2023. So almost exactly a year ago. I'm a professional space weather forecaster, and part of the work that Galen mentioned with launching balloons is actually part of that. And I run a website called spaceweather.com. Now, because I forecast space weather, I know when the good times are to look for northern lights. And in fact, from Aspendell, I have seen northern lights 7 times in the past 22 years, including on March 23rd, 2023. And so I'm going to tell you how you can do this too. Now, I went into my archives and I took a screenshot of, of another date in 2023. Anyway, last year in 2023, there were 2 big geomagnetic storms. One was in March and one was in April. Both of them produced auroras in California. And I took the screenshot because it doesn't have a very beautiful picture of an aurora on it, but it shows a map that shows how far down the Aurora Borealis went during that geomagnetic storm. And this is the border between Texas and Mexico. And so this is this little red blob here with some purple rays shooting up out of it. That's a cell phone picture of auroras on the Texas-Mexico border. So just from looking at this picture, you know it's possible to see auroras in California. You just have to know when to look. Okay, so I said I'm a space weather forecaster. You may or may not have ever heard of that before. But so in California, we have Santa Ana winds, snowstorms, we have rain showers, we have tsunamis, not too often. But there are similar things in space. There's solar wind, there's geomagnetic storms, meteor showers, and solar tsunamis. And space weather is a branch of science that's kind of like terrestrial meteorology, where we study and forecast these events just beyond Earth's atmosphere. And the Aurora Borealis is an aspect of space weather. Now, most space weather comes from the sun. The sun is so big, a lot of people don't know this. The sun is so big, we actually live inside the sun's atmosphere. And what protects us from it is the magnetic field of the Earth. And this graphic, not to scale, shows the sun, here's the Earth, and all of these lines out here, this little force field is the magnetic field of the Earth. It's the same magnetic field that when you look at a compass, it causes the needle to point north. But it also protects us from when things explode on the sun, they don't come down and hit us right on the Earth's surface. They hit Earth's magnetic field first. And this picture of the sun shows a lot of activity on the sun. Here's an explosion, that's called a solar flare. This big giant bubble of plasma coming out, that's called a coronal mass ejection. And these little black dots right here are sunspots. So we're going to understand how all of these things make auroras here in California. But first, let's take a look at sunspots. This is last month, February 2024. And it's this isn't 12 different sunspots. This is a stack of daily images of the sun. And so this is the same sunspot marching across the sun over a 2-week period. And so this sunspot right here actually, it's the biggest sunspot in about 50 years. And part of the sun is missing down here, but there's a lot of sunspots down there too. Sunspots, they look like they're made of matter, but they're not. They are islands of magnetism that are floating on the fiery surface of the sun. So they're actually giant islands floating on this sea of basically flaming plasma, okay? And
they're gas also?
Sorry?
They're gas also?
No, they're made of magnets. This is kind of what's a little bit mind-bending about this, is that the same material that makes up Earth's magnetic field, which is no material at all, but a force field, is the stuff that makes up a sunspot. And the reason it looks dark is because it's not allowing heat and radiation to flow up from beneath the surface of the sun, so it looks dark. But it's like this island, this knot of magnetic fields, and they're really big too. Here's an amateur picture of that sunspot, and the photographer who took it put some pictures of the planet Earth along the bottom so you could get an idea of the scale of the sunspot. And here's another picture, that, and I mentioned this sunspot appeared last month. This was taken up in Canada on February 25th. Here is the sunspot at sunset, and the photographer didn't use any kind of filter or telescope or anything to see it. He just let the sun set into the atmosphere and it dimmed, and he took his camera and took a picture of it. So these sunspots can be 10, 20, 30 times the size of our entire planet, and you can actually see them with the unaided eye, but only if you manage to dim the sun down enough that it doesn't hurt your eyes. I brought some eclipse glasses to hand out to everyone, and it's dark in here, and I don't know if you can hand them out right now, but it would also be okay. I think it, yeah, okay. So we're going to hand these out. Now, through these glasses, and in fact, you can put them on. Wait a minute, don't put them on yet. Let's get them all handed out. When these sunspots are crossing the face of the sun, you can actually put on these glasses and look up at the sun, and you can safely see the sun will just turn into a disk. It doesn't hurt your eyes, and you can see these sunspots on the surface of the sun. The reason I have so many eclipse glasses right now is, do you know that there is going to be a total eclipse of the sun next month?
Yes.
Okay, on April 8th. And just so you know, it's not going to be total in Bishop. You will have to travel to the path of totality to see the total eclipse. And the path of totality stretches, I don't have a graphic that shows it, but the path of totality stretches along a 100-kilometer wide corridor from Texas to Maine. So if you want to experience totality, and I highly recommend it, you need to go there. But if you stay in Bishop, you have your eclipse glasses, and if you look up at the sun on April 8th, you will see that about 50, it'll look like a crescent. It won't look like a sphere, it'll look like a crescent. And you may see sunspots on that crescent as well. So the eclipse is not total here, but there will be a partial eclipse in Bishop. Okay, that intermission was just I didn't know what the situation was going to be, so I kind of imagined I might be handing out these eclipse glasses. And if the lights were on, I was going to have you all put them on at the same time and take your picture, but maybe at the end. Okay, so sunspots are important because they love to explode. And during the question and answer period later, if you want to know why they like to explode, I'll explain. But for now, all you got to know is sunspots are like dynamite. They like to explode. And when we see big sunspots like that on the sun, space weather forecasters are like, okay, you know, there's a chance of there's a chance of a big solar flare today. And the bigger the sunspot, the bigger the flare. Now, everybody's heard of solar flares. Here's an example of a solar flare that actually occurred. This is that sunspot I just showed you exploding. Now, here's another cool thing about sunspots. Unlike a stick of dynamite, when a stick of dynamite explodes, if you go back and look for the stick of dynamite, it's blown to smithereens, right? Because sunspots are not made of matter. That's not what happens. The sunspot explodes, and when this tremendous flash of light dims and you look again, the sunspot's still there. It's like that liquid metal robot in the Terminator, Terminator 2, where it just like reforms and now it's its old deadly self again, and another solar flare can take place. So you may wonder, oh, why does the sun look this funny color in this picture? This is a photograph from a NASA observatory in space, the Solar Dynamics Observatory. And the solar physicists love to look at the sun through filters that show extreme ultraviolet radiation, because it is at those wavelengths, which some birds can see but we cannot, that solar flares look really bright and dramatic. Okay, so would you turn the sound down, Galen? Thank you. So I just showed you there's an explosion happening, right? Well, these explosions do produce debris. And the debris from the explosion of a solar flare is called a CME, which is an acronym that stands for coronal mass ejection. Now I'm going to show you, this is a NASA movie. So what we see, I'm going to pause. Oh, darn.
Yeah, no, that you just shows.
Oh, okay. Darn it. Sorry about that. Okay, so all the stuff you see first, that's solar wind. That's just normal. The sun's always blowing this wind. Now it showed, this is the Earth's magnetic field that we saw in an earlier graphic. I'm going to play this movie one more time, maybe. There we go. Now, the Earth always has its magnetic field. It doesn't just grow right before a CME comes. So did you see how when the CME hit the Earth, or it hit Earth's magnetic field, our magnetic field kind of shook? Kind of like go into your refrigerator, and if you have a tray of Jell-O, thump it and it shakes. That's exactly what the magnetic field, our planet's magnetic field, shakes, and it reverberates from the impact. And while the magnetic field is shaking, that is what we call a geomagnetic storm. And if you had a sensitive enough compass, and especially if you were up near Earth's polar regions, you could look at your compass and see the compass needle shaking during that time. The magnetic field all around you is shaking back and forth, and also up in space, all right? Now, meteorologists, everybody's heard of the 5 different categories of hurricanes, right? 1, 2, 3, 4, and 5. Well, NOAA actually has, not only do they track terrestrial weather, but they have a space weather prediction center also. And they have 5 categories for geomagnetic storms. All 1 through 5, G1 through G5, okay? And you know those auroras that I showed you in the very first slide from March of 2023? That was during a G4 geomagnetic storm. And you see, this is not entirely true. It says auroras may be seen as low as Alabama, that's true, in Northern California. I would say during a G4, you can see auroras if you're in a dark sky site all the way down to Southern California. A G3, so G1s are very common. G5s are pretty rare, and we'll get into that a little bit more later. A number of G3s have happened in the past 3 years, and from here in California, if a G3 storm is underway, you can definitely photograph the auroras. I mean, not if you're standing under a streetlight in Bishop, but if you drive up to Aspendale, for example, you could definitely take a beautiful photo of the Aurora Borealis when a G3 is underway. And G4 and G5, G5, I've seen G5 storms in Aspendale, and you will think you're in Alaska if you know when. A lot of these things happen and nobody even knows to walk outside and take a look. But during a G5 storm, there have been auroras in Mexico, Cuba, Tahiti. From our latitude in California, you can see green curtains of light rippling across the sky. You just have to kind of know when to go outside and look.
How long do they last?
It depends. Sometimes they are short-lived, and that here at low latitudes, the peaks of the display can be short-lived. Up around the Arctic, if you have a G5 storm, up around the Arctic Circle, they'll be reading newspapers by auroras for days. Here, we might just have a window of 1 or 2 good hours when you should rush out and take your camera. All right, let's see what's next.
Do we know when they're coming? Is there a prediction that you know?
Oh, absolutely. Yeah, we 100% know when they're coming. Yeah, I'll talk about that in a little more detail later, but the answer is yes. It's often said that space weather forecasting is about 50 years behind terrestrial weather forecasting, so you can go on Weather Underground and look for a 10-day forecast for snow and stuff. We really only have like a 2 or 3 day forecast for space weather, and so we can predict CMEs a few days ahead of time, but we can't tell you, like, what's today, the 14th. So maybe a CME is leaving the sun now while I'm giving this talk. So I'll see that and I'll say, okay, that looks like that CME is going to hit Earth on March 16th. Be a typical CME, takes about a couple of days to get here. But nobody can tell you what hour on the 16th it will hit. So that's how far behind our computer models are. So 50 years from now, we'll know exactly when, but now it's just on a day, you know. It would be like if somebody said, oh, a Category 5 hurricane is going to hit Florida sometime within the next 24 hours. Well, you better leave immediately. So sometimes people ask, hey, what's the difference between a solar flare and a CME? And I kind of already explained, solar flare is the flash of light from the explosion, and the CME is the debris. And for an atomic bomb, like an atomic bomb on Earth, the mushroom cloud would be the CME, and the flash of light when the bomb explodes would be the flare. So that is the difference between the two. Now, when a CME hits Earth, this happens. We get the Aurora Borealis. This is a picture from, March 24th, 2023. This is what the sky looked like in Finland when Mammoth had those kind of reddish purple auroras over it. So you can see that you still might want to go up to the Arctic Circle to see the auroras. I think the next slide is a movie. And is the volume still turned down? Okay. This movie has some really dramatic music. It might scare you. But the movie that we're going to see was recorded by a friend of ours who runs an Aurora tour guide service inside the Arctic Circle in a town called Abisko, Sweden. They have a meteorological phenomenon over Abisko, which the local people call the blue hole. So when the rest of Scandinavia is blanketed by clouds, they have this weird little swirl that, from winds coming over the mountains in Norway, that literally make a hole in the cloud cover over Abisko. And so it's like one of the greatest places in the world to go see the auroras. And I'm just going to play for you. This movie is from December of 2023. This, you can see these dark things. Those are clouds, so they're actually seeing auroras shining through the clouds. These are the city lights of Abisko down here. And in a moment, we're going to see the auroras become so bright that the entire landscape turns green. And that phenomenon of the snow beneath your feet turning green is not an artifact of the camera. It's something you can actually see with your unaided eye. These are just curtains of auroras overhead, and do you notice these little ripples right here? These are, in a moment, we're going to turn the lights on, and I'm going to draw a little diagram on the whiteboard. Okay, here's something I want you to notice. You notice how these auroras are green on the bottom and red on top? That's going to be something we're going to talk about later. And once again, you see the auroras become so bright that the snow starts turning green on the ground below.
And is this like a little time lapse?
Yeah, this is, yes, this is a time lapse. And I don't know how much time is in this. Probably like 20 minutes of time compressed. When you look at, sometimes when you look up at auroras from the Arctic Circle, you will see a lot of fast-paced dynamic motion during a thing called a substorm. But then a lot of times it's very leisurely. Okay, so auroras can be very leisurely, and then you have to speed it up to see that.
So those ripples, you were saying they were all like ripply?
Did you notice that little ridge of fine structured ripples? I'll explain those now. Could we turn on the lights for a minute? I'm dying to write on a blackboard. So we'll see how this goes. So I want to explain to you what happens to cause the auroras, okay? And this is a simplified explanation, but it's totally good enough. So imagine that the Earth is flat, or that you're just on a very big planet. And here's the atmosphere. Oh, actually, I'm sorry. I want to start with a different idea. That the Earth is round. We've seen some pictures in these movies of how the Earth's magnetic field looks. So these lines that I'm going to draw are called magnetic field lines. They show the shape of Earth's magnetic field. And if you wonder what this means, you could think back to school in science class when you had a bar magnet with a north end and a south end. And one thing that sometimes you do in science class is you'll put a bar magnet on a table and sprinkle iron filings around the bar magnet. And then you actually, the iron filings line up with that same kind of shape. So the Earth, our entire planet, is a gigantic bar magnet. Not as gigantic as some other bar magnets in the solar system, but it's basically a gigantic bar magnet. And these are lines of magnetic force, okay? Here they go. Now I'm going to do one more thing. I'm going to draw little arrowheads on these lines, okay, to give these lines some direction, all right? And later, when we talk more about the secret tricks for seeing auroras in California, these little arrowheads are going to become important. But you may say, well, what do these arrows mean? Well, basically you can think of it, I should have brought a compass, that if you're standing on the Earth's surface with a compass, the arrow on the compass is going to point in the direction of these arrows. So this is our North Pole, and this is our South Pole. So the arrows are coming out of the south, and they're going into the ground up north. Make sense? Okay, so I talked to you about the coronal mass ejection, the debris from when a sunspot explodes. A coronal mass ejection is kind of a mixture of broken up hydrogen atoms that have actually just been broken to pieces by the explosion. And the coronal mass ejection also has some tangled magnetic fields within it. So the particles that are in those charged particles, electrons and protons that are in the coronal mass ejection, when they come down to the Earth, they're going to hit Earth's magnetic field. When one of those particles hits out here, sorry, I'm drawing a lot of blue things. I'm going to change colors. So these are particles. Here's a particle, and it's rocketing in towards the Earth. It's part of the coronal mass ejection. It's a charged particle. It's an electron. And our magnetic field does a good job repelling that particle, making it bounce off. It's like a force field around the Starship Enterprise in Star Trek. That's what we have. We've got this force field around our planet. But our force field's not perfect. It actually has a couple of weak spots, and those weak spots are near the poles. Because whereas this charged particle will kind of bounce off down here, this is the equator, by the way. Here's California. We don't know what California looks like. But so the charged particle really has trouble getting into that's California. Charged particle has trouble getting into California. But charged particles that, let's say, come up here, they get guided into the poles. They can come down and reach the poles of the Earth, okay? And when these charged particles, so one important thing I left off this diagram was our atmosphere. Here it is. This is the purple gas that you breathe. So when charged particles come and they hit the atmosphere, it makes the air glow. And for certain members of the audience of a certain age who remember the original color TVs, electron beams would hit the front of a picture tube and make it glow, and that's where the picture came from. All right? Exactly the same phenomenon is happening here. These beams of electrons are being funneled towards the poles by Earth's magnetic field, and these electrons hit the atmosphere and they just make it glow. And the colors in that movie come from the glow. Okay? That's all. Simple as that. Okay. Yeah, thank you. I'm pretty sure I have not written on a blackboard in 30 years. So that is why, for the reasons I just explained, that's why auroras tend to be concentrated around the poles, and they tend to form an oval shape, and it's called the auroral oval. This is just an artist's conception of the auroral oval. These are pictures for actually pretty early in the space age. Satellite was launched which had an ultraviolet camera on it because people had never seen auroras from above, right? We only ever saw them from below. So one of the first cool things that was done in the space age was to go up and see what do auroras look like from space. And you can see this was during a geomagnetic storm. And in this case, the auroral oval had expanded. Up here, it's concentrated up in Canada. Here it had expanded a little bit. It was down in the Great Lakes region, and looks like actually there were some auroras getting down into Florida. And one of the big discoveries at that time, nobody knew for sure, was that were northern lights and southern lights the same thing, and did they occur at the same time? And so here we see that, yeah, that's Antarctica. So you've got an oval around Antarctica as well. And now it's understood that when we have a geomagnetic storm that's making skies light up over the northern hemisphere, the same thing is happening in the southern hemisphere. And actually, sometimes the correlation is quite detailed to where when you have a flare-up at a certain place here, you'll have a conjugate flare-up down here. The auroras are actually very connected between the two poles. Oh, we did that because I don't know what slide is coming next. So that was the intermission. That was the chalkboard. Okay, so now that we understand the chalkboard physics, this is actually a, I mentioned earlier that NOAA has a space weather prediction center. And this is one of the things that they publish actually every 10 minutes. And they'll show you where the auroral oval is right now. And so this was earlier. So I put this in the slide deck earlier today, this morning, or 1800 Universal Time. And right now, today, things are very quiet. And so the auroral oval is very small, and you'd have a hard time finding auroras today. Look at this. This is the probability of auroras. If you went all the way up to Greenland and Iceland, you would still only have a 10% probability of seeing auroras today, because things today are just very quiet. You know that place, the movie I showed you, and I said Abisko, Sweden is like the world's greatest place to see auroras? It's right there. So even today, on a very crappy day, they're probably with cameras taking pictures of auroras up there right now. California, you recognize it from my map right here. Right now we are thousands of miles away from the nearest auroras. But sometimes during geomagnetic storms, one of the things that happens is that one of the things that happens is the auroral oval gets a lot bigger. It expands, and the auroral oval can expand down to our latitudes. And here's an example. March 23, 2023. So this was last March. I want you to notice that these auroras, this is the same storm where auroras were seen over Mammoth. This is over the Shenandoah National Park in Virginia, okay? And they see a beautiful band of green and also some red auroras up here. So that's just an example of how the auroral oval can expand. I told you that particles from CMEs get funneled in towards the poles. But if the CME is ferocious enough and the particles are energetic enough, they can burrow through Earth's magnetic field all the way down to Virginia and California and Texas and places like that. Okay. See, I really have to check the dates now. So this is March 25, 2023. This was the morning after the Mammoth Lakes auroras. And so I just printed this screenshot out of what I was writing on my website the next morning after we had had auroras here. And I had photographed, this is a 5-year-old Galaxy Samsung. I used my phone on March 24th to photograph auroras over Aspendell. so that was one of the 7 occasions that I mentioned earlier. So my website is actually intended for a somewhat technical audience, but I'm going to read this introductory paragraph, and I think already you're probably beginning to understand some of the jargon that we use as space weather forecasters. It says, forecasters did not see this one coming. On March 23rd, auroras spread into the United States as far south as New Mexico. Later, I would revise that to even lower latitudes. During a severe Category G4 geomagnetic storm. It was the most intense storm in nearly 6 years. The cause of the storm is still unclear. It may have been the ripple effect of a near-miss CME. And so that was confirmed later that some of these CMEs are so powerful that they don't even have to land a direct hit, and we get big storms. So this was a CME that did not hit Earth head on. We weren't expecting it to hit Earth, but it kind of grazed our magnetic field, but yet that was enough to send auroras all the way down to our latitudes. This is a picture that somebody sent me of, so it says Mammoth Hot Springs, but don't get excited. It's not our Mammoth Hot Springs. These are the Mammoth Hot Springs in Yosemite at latitude plus 45. At Yellowstone, thank you. Yeah, in Yellowstone. Yeah, not in Yosemite. That would also be exciting to us. And then there are some links down here to the time I was writing this, a few other low latitude places: Virginia, Nebraska, Colorado, Missouri, North Carolina. I think by the time all the data was collected from this storm, that there were only about 6 or 7 states where people did not report seeing auroras. And Hawaii was one of them. Hawaii didn't see auroras. But I think Hawaii could have seen auroras during this storm. The reason they didn't was because you had asked earlier, how long do the storms last? The storm just died out before night fell over Hawaii and that they could see it. Okay, here's another example of some auroras in California. This was actually also one of the 7 cases of auroras that I saw. This is a pretty old example. This is from November 6, 2001. Here's auroras photographed in San Jose, auroras photographed in a park near downtown San Diego, auroras photographed from Mount Laguna, just outside San Diego. I think Mount Laguna is just outside San Diego. So one thing you may notice about these auroras is that they are all red. Oh, I was going to explain why, but it looks like we're going to take a quick detour. That's a cliffhanger. Why are auroras in California so red? Must be chemtrails. Well, let's go check out some other planets instead for a moment. So this is another. So the volume's down. Here's another movie. Here we see the solar wind. All right. Here's 3 planets we're going to take a look at. I don't know if I can pause this movie. First, we're going to take a look at Mars. CME is going to hit Mars. Notice that Mars. Oh, I wish I could. Darn it. Okay. Hang on. So one thing I want you to notice about Mars is it doesn't have a big magnetic field, and the CME seems to actually rip stuff off of Mars. Okay, I guess we'll talk about that when the movie's over. Here's the Earth. We've seen it before. Earth has a really nice magnetic field, and when the CME hits, it jiggles. See all the jiggling that's happening? Geomagnetic storm occurs. Now here comes Jupiter. Jupiter is actually 10 times bigger than the Earth, so this is not to scale. Here's Jupiter. Jupiter has the most powerful magnetic field in the solar system. Watch what happens when the CME hits. Nothing. Jupiter is very well shielded. That little outer boundary moved a little bit, but if you were down on Jupiter, you wouldn't know. You would be like, okay, that was a G0. Nothing happened. We have such a good magnetic field. So let's see what auroras look like on some of these planets. So this is 2 weeks ago on the planet Mars. These purple dots are a CME did hit Mars, and Mars does not have a magnetic field to protect it. So these charged particles that I showed you, they don't get funneled to the poles. They just rocket right down and they hit Mars, and they hit Mars everywhere. So when Mars has a CME strike, the auroras appear globally. So they're everywhere. So the day side doesn't show auroras. This is the night side. And this is a picture taken by NASA's MAVEN spacecraft, which is orbiting Mars now. And it's an ultraviolet image, okay? Auroras on Mars shine at ultraviolet wavelengths. So if you were there, you would not see them because our eyes do not see ultraviolet light, okay?
Why are they ultraviolet on Mars?
They're ultraviolet on Mars because here on Earth, the different colors of auroras come from different atoms and molecules at different temperatures and densities in the atmosphere. So a few slides from now, I'm going to explain how red auroras come from oxygen at the top of the atmosphere where the density is very low, and green auroras come from the same oxygen lower in the atmosphere where the density is high. So the density of the gas tunes the color of the auroras. That's one of the factors that determines the color of the auroras. The atmosphere of Mars has a different chemical composition from that of the Earth. It's mostly carbon dioxide. And so when these particles come down and they hit, the carbon dioxide is creating these ultraviolet auroras. Ultraviolet is just a different color. So on Mars, if we have astronauts on Mars one day, they will not see the Aurora Borealis with their naked eye. They can't. But the auroras do exist. All right, let's go to it's a movie. I forgot that. So here's some auroras on Jupiter. Now, okay, you may be saying, wait a minute. We just saw that Jupiter has this incredible magnetic field that doesn't even quiver when a CME hits. How is it possible that there can be auroras on Jupiter? Okay. On Jupiter, there is a moon, here's a couple of the moons of Jupiter. Right over here, there's yet another moon called Io, which has active volcanoes. And these volcanoes put our volcanoes to shame. They are mega volcanoes. And when they erupt, they send plumes of debris up into, and they act just like CMEs. These volcanoes are so powerful that when they explode, it's like a solar flare for Jupiter. And the debris from these volcanoes goes up Jupiter's magnetic field and get funneled toward the poles. And when it lands on the poles, you get volcanic auroras. Wow. So Jupiter has auroras, but it doesn't come from the sun. One thing we'll note is that these are pictures of auroras on Jupiter for some of the same chemical reasons we were just discussing. Do not shine in visible light. They tend to be bright in the infrared. And also, I don't know if it says it on here, but anyway, these are ultraviolet. This is a picture from the new James Webb Space Telescope. This is a picture from the old Hubble Space Telescope. This is ultraviolet. This is infrared. So once again, if you were an astronaut looking for auroras on Jupiter, your eyes are just wired wrong. You wouldn't see them. Weirdest auroras in the solar system are on Mercury. Mercury is very close to the sun, and So CMEs are really harsh on Mercury. They hit Mercury point blank range with full force, and Mercury does have a magnetic field, but Mercury still is practically defenseless against these ferocious solar storms. The particles go and they just hit the ground everywhere, and they hit the ground with so much energy that it creates X-ray auroras. If you were on Mercury, you wouldn't look up in the sky to see auroras. You would look down at your feet and you would see your bones, because it's an X-ray machine. Not good. It would not be on your bucket list, or let's just say it would be at the end of your bucket list. Okay, really just had to mention auroras on Saturn. Here's another Hubble image. Saturn has polar auroras. In this way, Saturn is a little bit like Earth in the sense that the sun does make auroras on Saturn. Saturn has a magnetic field, but it's not as tremendous as Jupiter's magnetic field. So auroras are polar, just like they are on Earth. But once again, the auroras are ultraviolet auroras. They're not visible light auroras. And in fact, this is a fake composite picture of a little... There's one picture that shows the ultraviolet auroras and everything else is black. And then there's one picture that shows the rings in the planet in visible light, and they put them together. That happens all the time with Hubble photos. Don't believe these things. Okay. Okay, so the conclusion is we're actually pretty lucky to be able to see northern lights on our planet the way that we do. I mean, there's no evolutionary reason that our eyes should be tuned to the same wavelength as auroras. It's just good luck that auroras on Earth emit a lot of photons that our eyes can pick up in the visible part of the spectrum. So I guess we went on that detour so you would realize how lucky you were. Now, auroras, we're going to get back to the cliffhanger of why are auroras in California often red. So auroras on Earth are like a layer cake. They have red icing and green dough, red on top, green on the bottom. And I explained that a moment ago, that oxygen at different altitudes in our atmosphere glows a different color depending on how high they are, how hot or cold they are, and how dense the gas is. And here on Earth, the auroral oval, it's like it has red hair and a green body. It has two layers. And this is significant for our aurora viewing in California. You can see that same layer cake structure in this picture from Virginia, red on top and green on bottom. But I don't know if you may have noticed, but back when we were looking at the Arctic auroras, it seemed like everything was green, right? And as we go to lower latitudes, we're beginning to see more of the red top. So if you turn the lights on for just a second, I think I can explain. This is evidence that the Earth is not flat, actually. Because let's say here's the Earth. I think I might make it a little rounder. I don't have a green pen. Do you have one? Okay. Thank you. Yeah, maybe Bishop might be here. So here's Bishop, and here's Abisko, Sweden, place with the great blue hole. So in Abisko, so in the atmosphere of Abisko, I'll make it a little taller, the bottom layer of the auroras is green, and the top layer, which I didn't tell you before, but the icing layer does tend to be quite tall compared to the green lower layer. So if I'm here in Bishop and I'm looking, and say there's some auroras up in the north at northern latitudes. And by the way, that is like a pro tip, look north, okay? That will help. So let's say I'm in Bishop and I'm looking north, and so I'm looking at these auroras. If you're looking at auroras that are to the north of you, the green auroras are often blocked just by the body of the Earth. They're eclipsed. So you tend to see the red, here at low latitudes, you tend to see the red tops. Now, reflect back to the movie we saw of the auroras in Abisko that were like all green everywhere, right? The ground was turning green, everything was turning green. Well, that's because they're looking straight up into this, all right? And another factor is that the green does tend to be intrinsically much brighter than the red, because there's a lot more air close to the Earth than far from the Earth. So you have a lot more oxygen atoms and molecules producing the green, and you have relatively few oxygen atoms producing the red up here in the outer atmosphere. Does that make sense? Okay, so now with this in mind, you can not only understand why most auroras in California look totally red, but moreover, that if you do go out during a geomagnetic storm and if you see green, it's here. It's right on top of you. You're not looking at something that's happening in Canada. You're looking at something that's happening right here. And I have seen a storm like that. It was on August 12, 2001. Like, I don't know birthdays of people in my family, but I remember August 12, 2001, and it was during the Perseid meteor shower, and we were on our front porch in Aspendell with all the lights on, and all of a sudden green auroras started rippling across the sky. It was like we were in Alaska. So just to give you context, I said I've seen auroras 7 times in Aspendell. 6 were all red, and 1 was green and red in like 22 years. So that gives you a sense of your odds if you know when to look. Okay, we can turn the lights back off. Let's see what's next. Oh, okay. Yeah. So in California, we mainly see the red icing on top. That's what we see. So now I want to start giving you the information that you came for, which is how do you do it? How do you know? Well, you can see auroras in California when there's a G4 or G5 class geomagnetic storm. Okay, it's also got to be dark outside. I mean, I know that sounds like it's duh, but honestly, for most of the red auroras that we see in California, you need really darks. You need to go to you come to Aspendell and stand out under the stars and let your eyes dark adapt. And a lot of these red auroras, which I've told you are kind of faint and whatnot, you can see them with your unaided eye, but you're not going to see them on Main Street in Bishop. So darkness definitely helps. They also happen when cracks appear in Earth's magnetic field. That's something I haven't talked about, but this is the real secret. This is how I do it. Intermission. We're going to go back to the blackboard for a minute.
You couldn't leave us hanging on that one.
No, I'm going to explain it.
Oh, yeah.
Yeah. Okay. Now, we've talked about CMEs. They're the debris from the explosions. They contain a lot of charged particles, but that's not all they contain. Remember, I told you they come from sunspots. When sunspots explode, sunspots are made of magnetism. So these CMEs carry some of the sun's magnetism to us. It is actually basically a piece of the sunspot ripped off and coming to us. So let's draw, like, okay, here's the CME cloud that's coming, right? And so it's got a lot of matter in it, the stuff that you're familiar with, but it also has some magnetism, all right?
What do you mean when you say magnetism?
It's like a force. Just think about Star Trek. It's like the force field around the, I mean.
It's molecules.
No, it is not. It is an insubstantial field of force. That's the universe we live in. It's actually not weird. I mean, the electric forces between the electrons in your body and the chair keep you from falling through the chair. It's the same thing, same kind of thing. You're in contact with it right now.
So it is electrons, though.
No, it's not even electrons.
These magnetic fields are supported by the motions of electrons. When charges are in motion, they create a magnetic field. But a good intuitive way to think of magnetic fields, which is actually, even though it's a kind of a cartoon, but it also is a physically correct cartoon that many physicists use, you think of them like a rubber band. If you twist a rubber band, it gets a lot of energy in it. If you pull it and let go, it snaps and it hurts you. That's a solar flare, okay? When the rubber band snaps, part of it can fly off and come towards the Earth, okay? And I've shown this magnetic field / rubber band as a really twisted up thing inside. So if you took your compass, you're an astronaut in a spaceship, you take your compass, something all astronauts do, and you fly out into the CME, and when you got out here in the CME, oh, it would be super confusing, right? Because no matter where you put your compass and it point this way and then that way, that's a very twisted magnetic field, okay? So some CMEs are like this. They come, they have twisted knots of magnetism along with all these charged particles and plasma, and it's going to hit the Earth. Okay, but they're not always this disorganized. Sometimes, I'm going to go red because this is blue. Sometimes, let's say that the magnetic field looks like this. And it has arrows that aren't pointing up, but are pointing down. Right? Now it's not a tangled mess anymore.
What would make it so organized?
Well, maybe the piece of sunspot that got ripped off was itself a very strong and organized piece of the sunspot. Okay? This actually happens. This definitely happens. And you have seen pictures of it happening in my talk. Because look at this. The arrows are pointing down, right? Now here, the arrows are pointing up. When you have an arrow that points down, meet an arrow that points up, they cancel each other out. Poof. So when this particular CME makes contact with Earth's magnetic field, it actually cancels our magnetic field because they're pointing in opposite directions. And it creates a hole or crack in the magnetic field. Now, look, the Klingons just blew a hole in our force field, okay? All right, you know how Data's always saying, oh, Captain, the shields are down to 17%. Okay, here we're down to like 80%. Here we're down to 50%. Okay, you get the idea, right? Then all of a sudden, well, let's pretend that California is over here. Now, instead of having all these particles coming into the poles, they have a direct line to the Eastern Sierra, okay? So we have satellites that sit out in space and measure the magnetic field of CMEs that are approaching us. And we can tell whether it's pointing down, south, or north, up. So this was the case where the CME can blow a hole in our force field. But you can imagine an opposite case as well, where what if I had drawn this in the other direction? Well, that can happen too. And in that case, the two arrows are pointing in the same direction, and instead of lowering our defenses, they strengthen our defenses. So a CME, even a big ferocious CME, is not always going to make auroras in California. It depends on what kind of magnetic field is inside the CME. Okay? You can turn the lights back on. Yeah, there are actually a couple of satellites. One is quite old now, 45 years old, and one's about 15 years old. So we have two satellites. One's called ACE and one's called Discover that do that work. Okay, so how do you know when these things are? So I said the trick is to know. Because you don't know, I know, but you don't, when these things are happening. So, and I want to preface this by saying, I'm actually not trying to earn money from you, and you'll see in a moment. I'm going to give this to you for free. So we have this service called spaceweatheralerts.com. If you sign up for it, you will get text messages when these events are happening, when geomagnetic storms are underway. And so if you go to our website and sign up, you can put in this code, White Mountain Research Station, and it will give you 3 free months. And you will get text messages when there are cracks in Earth's magnetic field and when geomagnetic storms are happening. You have to get the magnetic crack alerts, pick the pro plan, okay? Because now you're pros. But pick the pro monthly plan. That will ask you to enter a coupon code, and then you can try it for free for 3 months. Now, it turns out this is a good time to try. And I don't know if you've noticed, but a lot of the pictures I've showed you, notice they happen in March and April, right? There are certain months of the year that are better for auroras than others. And that was the next slide. This is a 75-year study of geomagnetic activity and how it depends on what month it is. And March is the most geomagnetically active month of the year. Close second is October, third is April, fourth is September. Now, I'm not going to explain this in detail, but I just want you to know that the physical reason for this is that, you know, Earth is orbiting the sun, and so the tilt of our magnetic field varies back and forth throughout the year with respect to the sun. In months around equinoxes, that is the time when these cracks I told you about are most likely to form, because the arrows can line up around the equinoxes. So March and April are the times when we're March, April, September, October. Those are the times we're most likely to see auroras. If you want to use that coupon code in the fall instead of the spring, wait until September. Go and type that code in September, because we'll have a 2 or 3 month period when our odds are better of a big storm happening. And the other thing that happens near the equinoxes is that around equinoxes, even wimpy CMEs do a good job sparking geomagnetic storms. You know, I read that passage to you earlier where I said the CME didn't even hit Earth. It just passed by the Earth. And that actually was the cause of those auroras over Mammoth Lakes. So feel free to enter that coupon code. Either do it in the spring or do it in the fall. Also, another big factor that makes this a really good time to look for auroras is the solar cycle. I told you about sunspots earlier. And we've known since the 18th century that the number of spots on the sun waxes and wanes with an 11-year period. And this shows I think I showed the space age here. These are different solar cycles in starting approximately in the space age. So I was born right between solar cycle 19 and 20. All right, and today we're in solar cycle 25. And you'll notice that solar cycle 25 is ramping up right now, okay? And when a solar cycle is near its peak, that is a time we call solar max. So we are now approaching solar max. Contrary to what you might see in like articles online and stuff, solar max is not, if they may say solar max has arrived, no. Solar max is a period of time that actually lasts for years. So we're just at the beginning of the maximum of solar cycle 25. So for the next 2 to 3 years, we're going to have a lot of sunspots and a lot of solar activity. Same plot, but just more detail on recent solar cycles. You remember the green auroras I saw in Aspendell on August 12, 2001? That's right here at the peak of solar cycle 23. Solar cycle 24 was pretty quiet. And actually, I saw a lot of auroras in Aspendell in 23, very few in 24. And now I've already seen auroras twice in solar cycle 25. And we have at least 3 years of high solar activity ahead. The fact that it's March does not guarantee that auroras are going to happen. A sunspot still has to explode in March and hurl a CME in our general direction. But if it does that during the month of March, you're almost guaranteed to get auroras. April also. Okay. Gayleen, what time is it? Okay, so I'm going to stop.
Five slides left.
These are bonus slides.
Okay.
So I think I would rather take questions.
Entirely up to you, Tony.
No, I mean, you can ask questions. If somebody wants to ask about this slide, this was March 13, 1989. 35 years and 1 day ago today. And it was the biggest geomagnetic storm of the space age, happened in March, and it completely blacked out the power to almost the entire province of Quebec. And these are city lights on the eastern seaboard of the US. This is Quebec. Totally black, a lot of cold people on a long winter night. Okay, so but let's turn on the lights and take questions. Yeah.
What about magnetic field weakening and possible reversal? Is that a thing?
When you say is that a thing, if you mean does it really happen, the answer is definitely yes. It can happen. The Earth's global magnetic field has been slowly weakening for decades. So our planet's magnetic field is not constant and never has been. Our magnetic field comes from motions of our planet's molten core, and there's a lot of sloshing and waves and stuff down there in the core. And Earth's magnetic field today is not the same as it was a million years ago. I mean, even 42,000 years ago, there is evidence of a disruption in Earth's magnetic field that coincidentally, I think, is timed with the disappearance of Neanderthals from the fossil record. And so people say, oh, did a reversal of Earth's magnetic field doom the Neanderthals? I would say probably not, because what happens, so Earth's magnetic field definitely flips from time to time. I think the most recent uncontroversial example don't hold me to this, but I think it was 700,000 years ago. There was an event that people don't fully understand about 42,000 years ago. That was not a full reversal of the magnetic field. And so you will read in places that, oh my God, if Earth's magnetic field reverses, it's going to leave us defenseless, we will die. And that is definitely not true, okay? Earth's magnetic field reversing is a natural occurrence. It has happened many times in the history of life on Earth. Life has not gone extinct. And the reason why I'm totally not worried about it. If Earth's magnetic field flipped tomorrow, I would not worry. In fact, I would make so much money selling space weather alerts. I mean, because when Earth's magnetic field flips, this is what people think happens. Earth's magnetic field, I'll tell you when you read about it online, this is what you'll read. Earth's magnetic field will weaken and it will disappear, and then it will, over some period of time, grow backwards, right? So flip all these arrows. Like now the South Pole is going to be north and the North Pole is going to be south. And between those two times, you are going to be defenseless. Cosmic rays from supernova explosions will break your DNA, and solar flares will hit the Earth with nothing to protect us. And this is what all those stories completely miss. That's not how magnetic fields reverse. And so I want to tell you, the sunspot cycle, that 11-year sunspot cycle, every 11 years, the sun's magnetic field reverses. It flips. That is a normal, natural part of the sunspot cycle. The sun has the same kind of magnetic dynamo that our planet has, except on a tremendously larger scale. So when the sun's magnetic field reverses, it doesn't vanish. It just gets complicated. I'll show you what I mean. Because Earth's magnetic field would also get complicated during a reversal. It doesn't vanish. It gets complicated. Here's what I mean by complicated.
How long does it take for that reversal in the sun to happen?
Oh, like thousands of years. I got so excited about the chalkboard, I took I'm taking these home.
We'll send you a bill for that.
It's not like you're going to experience that flip.
So I said thousands of years, but I should also say that because we've never observed it, we don't know. You know, we look at tree rings. So that's how, and ice cores, because you can tell from isotopes of carbon when more cosmic rays were coming in, and that tells you about the configuration of Earth's magnetic field. So there's a lot that we don't know. So if Earth's magnetic field flips tomorrow and it takes 24 hours, don't come saying, I say, well, it was supposed to take 25 years, but, or 1,000 years. But what happens when the Earth's magnetic field flips, or any dynamo magnetic field flips, it doesn't vanish, it gets complicated. So here we have a simple magnetic field with a North Pole and a South Pole. During the transition, you're going to have south poles that sprout up here, okay? And north poles over here. Our planet's all of a sudden going to have like dozens of magnetic poles that stick up everywhere. And where field lines are close together, it's like if you're near one of these poles, you're safe. Magnetic field is strong. You're not going to get blitzed by a solar flare. So Earth's magnetic field suddenly becomes very complicated. And these magnetic poles that I'm talking about on the Earth are like sunspots. Okay, sunspots are like magnetic poles sticking up out of the surface of the sun. And when this transition is happening, funny magnetic poles start to pop up everywhere, and the field reorganizes itself. And then when all is said and done, it becomes simple and well-behaved again. But during that transition period, you have a lot of magnetic field around the Earth. It's just not as simple as it used to be. And why I said, oh, I would make a lot of money on space weather alerts is because now, okay, now you have to spend $2,000 and fly to Sweden to see the auroras. Not anymore, right? Just go to your nearest magnetic pole and it's not even cold, right? Yeah.
So in your slide where it was talking about the different severities of storms, it said at G1 that it could impact migrating animals. Is that just birds, or does it also include sea animals and land animals, and how does it impact them?
It impacts any life form that can sense magnetism. And the types of life forms, I mean, if you had asked me, well, or, you know, if you had asked some mainstream scientist 30 years ago that same question, they would say, well, you know, homing pigeons might be able to sense Earth's magnetic field, but that's controversial. Now research has shown that life on Earth, ranging in size from microbes to the biggest whales in the ocean, sense Earth's magnetic field. And people who fly, this was something that I learned actually at a visit to NOAA's Space Weather Prediction Center, is they get calls from people who own homing pigeons, and apparently really good homing pigeons are quite expensive, and they don't want, and they do these races across country. There's this whole community of homing pigeon people, and they do not want to release their pigeons if there's going to be a storm during the flight, because they sense the magnetic field and they get confused. Whales are beached during strong geomagnetic storms. There are many marine microbes that migrate according to magnetic field lines that penetrate the upper layers of the ocean. Homo sapiens are, like, it seems like one of the few species that are kind of walking around blind and, you know, barely know what's going on. But a lot of life on Earth is really tuned into this.
So it's very disruptive to them.
It's not necessarily, I mean, it said disruptive, but it's not necessarily, like you may say, well, you know, is an atmospheric river hitting Aspendale disruptive? Yes. But it's just something that we live with, and we don't go extinct or anything because it happens. And a lot of life on Earth knows how to cope with geomagnetic storms.
Well, as a pilot, magnetic compass is always changing. And right now, it's a few miles off of the Florida coast. At what point on the Earth does that get before, well, two questions. At what point does that magnetic north get that constitutes a reversal? And then secondly, wouldn't the animals adjust to that because it doesn't move real fast?
Oh, yeah, I mean, the drift of Earth's north magnetic pole is well documented. And you're right that, you know, like depending on where you are on, so Earth's magnetic field, even though I've drawn it like all smooth curves and stuff like that, it's a little weird and lumpy, even when no geomagnetic storm is happening. And there are tables which, like you're alluding to, depending on where you are on the Earth, you have corrections to, you know, where is north real? Okay, my compass says there, but I know from Florida north, I really have to add half a degree to the right, that kind of thing. And that the corrections that you have to make are different depending on where you are on the Earth. And there's something called the World Magnetic Model. It's a high precision magnetic model that's issued every 5 years and updated so that digital compasses can actually point to true north. But a couple of years ago, they couldn't wait 5 years. They had to issue an update after only 3 years because Earth's magnetic north pole is not only moving, which is normal, but it's accelerating. It's moving, it's like moving faster and faster. I think it's in Baffin Bay or something now, and it used to be like 30 years ago it was 500 miles away, and it's moving faster and faster, and the rate at which it's moving now is faster than we have seen before. But once again, I'm not really worried because we've only been tracking it for a couple of 100 years versus we know of massive regional and global changes on much longer timescales. So when you say, well, how far does it have to go before it's a reversal? Well, I would say it has to go around here, you know. But before it, before it gets there, a lot of this other stuff is going to happen. I mean, people in, I mean, there, for example, there's an interesting magnetic anomaly in Africa. Now, maybe 100 years from now, you've got a little North Pole sticking up out of Africa. That, to me, that says, okay, we're reversing now.
So the declination degrees that are on the old-fashioned printed USGS maps, those actually change over the decades?
Oh, yeah. Yeah, that's why, yeah, those old maps, those maps become obsolete after a period of time. These world magnetic models that they produce are hyper precise for military vehicles that get into situations where they can't use GPS, or if the GPS network were to be knocked out by a rival military or by a solar storm. Okay, that can happen. So they have these hyper precise magnetic models that allow vehicles to use the magnetic field for precise navigation. It's a backup to GPS. Yeah?
Speaking of knocked out by solar storms, what systems are the most vulnerable?
Oh, if we get knocked out by solar storms, did you say? All right. So every now and then you'll read about the Carrington event. On September 1st, 1859, a CME hit Earth. Well, the solar flare that launched the CME was so bright, people saw it with their naked eye. Especially a guy named Richard Carrington, who was a private astronomer working all by himself on a mountaintop. And so the event was named after him because he actually saw the solar flare without an ultraviolet filter, okay? And then nobody knew about CMEs in those days, but then like a couple of days later, boom, CME hit Earth. It was so powerful that telegraph stations, AKA the Victorian internet, telegraph stations caught fire. Okay, so it was the real deal. And so everybody's been quaking in their seats, like, when is the next Carrington event going to happen?
There hasn't been one since 1859?
There have been geomagnetic storms that were actually of similar magnitude since that time. There have been several, but we're just not as I mean, if one happens now, we're in big trouble because we're at the apex, as our civilization is at its apex of vulnerability to solar storms right now. I mean, if the Carrington CME hit Earth today, you would not be streaming this lecture on the internet for a long time, okay? Power grids have been reinforced to be able to withstand a Carrington event. Most high latitude power grids have installed protective hardware, especially capacitors, to help them not go down during a Carrington event. Low latitude power grids, like actually if the Carrington event happened today, I'd probably rather live in Sweden than Arizona, because people in the utilities in Arizona are not ready for what could happen, okay? We would probably lose a lot of internet capability because a lot of our internet is satellite now. the entire Starlink constellation of 3,000 satellites would almost certainly be destroyed by a Carrington-class event. Hey, in February 2022, now you know what a G1 class storm is? A G1 class storm brought down 22 Starlink satellites. Okay, and by the way, G1 to G5, that's a logarithmic scale. 5 is not 5 times stronger than 1. It's 10 to the 5th times stronger than 1. Okay, so we're quite vulnerable. So a lot of people say, oh, we're like one good CME away from being thrown back to the Stone Age. That's a bit of an exaggeration, but let's see. Okay, thank you. So this is on July 23rd, 2012, the Sun produced I apologize for the length of this movie near the end of the talk. The Sun produced a CME, here it is, that was every bit as powerful as the Carrington CME. This shows the week before that big CME. This is an artist concept of a CME. In a moment, we're going to get to the good part. So here we are. We're looking at the Sun from the Earth. That was the explosion on July 23rd that caused the CME. You can see it's just around the edge of the Sun, right? We're actually not seeing the solar flare. We're seeing the debris come out. It was just around the edge of the Sun. That debris that came out, now I think we're going to get a little video here of, okay, NASA had a satellite called Stereo-A on the opposite side of the Sun over the edge that saw the explosion that occurred. So now we see the solar flare. And now we're going to see the CME come out. And this was from a spacecraft that was looking down on the CME. All of this snow that you see there's the cloud, right? Now we see a lot of snow like on an old TV set. Different satellite, the CME appears to go in a different direction. All that snow is particles accelerated in the leading edge of the CME, striking the camera and fogging it. We're going to get to a really dramatic, you probably think this is dramatic so far, and it is. That CME completely fogged the cameras on that satellite. These are just more pictures of the CME. This is called a coronagraph. It's a type of device that makes an artificial eclipse of the Sun, so you can see these CMEs coming out. The time that CME occurred, here we go. Okay, there's a CME that hit Earth. That's a normal CME, made a nice geomagnetic storm. Here's a few more CMEs coming out in the days that followed. And there's the big one. Half of the solar system had the CME pass through it. Look how big it is. And look how close we were to being hit by that CME.
This is all actual footage.
Yeah, that was all real. Here's a computer model I'll just play while we talk. Normal CME caused, actually I think that was a G4 class storm. A little tiny CME came off, normal day, then boom, this thing happened. So it missed us, but if it had happened about 5 days later, Earth would have been further ahead in its orbit and would have been hit head on with that CME in 2012. And so, I mean, that just goes to show you, okay, we'll just let that play while we conclude. I mean, that just goes to show you that these big events are still happening today. And sometimes we're just lucky that we don't get hit. You know, and space weather, these CMEs, the little ones produce this, but the big ones produce darkness. Were there any other questions?
Have they been able to measure the reach of a CME into space, like how far it goes?
Yes. The Voyager spacecraft at the edge of the solar system have been hit by CMEs, and they take more than a year to get there. So a CME takes a couple of days, 2 or 3 days to get to us. If it's only 1 day, we're in trouble because it means it's a fast one. Typically 3 days. They kind of slow down as they propagate out. And then they've been seen by both Voyagers and one of the Pioneer spacecraft.
So it's actually particles that are.
It's the same mix of particles and magnetism that we get at Earth, just kind of tired by the time it gets out there. Okay. Thanks.
Do you want to take a picture with everybody?
Oh, yeah, totally. Is it glasses time?
Put on your glasses. You know how some speakers imagine the audience in their underwear to make themselves feel comfortable? This is the next best thing. Okay, thank you.